Now we will see the NPN transistor as a common emitter amplifier. So the arrangement, so this is your transistor NPN. So this is collector, base, emitter. Then the next thing, their terminal are taken out. The one is connected between VBE, the another is connected between that collector and ground. So this is how we are just going to see the arrangement for the same. The IB, IC, they are just approaching over here, and this is your IE. Yeah, so this is again VCE, this is IC, RL, and this is how it looks like, the amplified your wave. But obviously you can say that there is a phase shift of now 180 degree between input and output signal. Yeah, so that is how it looks like. So the input section is forward bias and the output section is a reverse bias with the polarity of that. So you can say that. So this is how it will occur. Again we just say that your IE is equals to IB plus IC. Yeah, so the phase relation between the input, and you can say one more thing. Yeah, obviously that Kirchhoff's law you just applied over here, and for this case you can write it down, that is your VBE, and again similarly you can write it down, that is your IBRB if there is some resistance. Yeah, and that VBE is equals to 0 for the input side, and for output side again that VCC minus VCE minus ICRC, that is also equals to 0. So these are the two equations that also you can write it down. So you can say thus this during the positive half cycle, obviously there is a phase shift of 180 degree. Yeah, so the input output differs by your 180 degree, and the negative half cycle also the same thing happens over there. So PNP transistor as a common emitter amplifier. So the same thing we can prove for this case also. Just this is the arrangement, so which how we can show IE is equals to, that is again IC plus your IB. Yeah, so similarly you can represent, you can just prove that there is a phase shift of 180 between your input and output. Yeah, so the same thing that we have mentioned, the gains in common emitter amplifier, that beta, that is IC upon IB. Yeah, and for AC current, that is IC upon that delta IC upon delta IB. Yeah, so this is AC current gain and DC current gain. Obviously AC voltage gain, so that is a change in the output voltage upon the change in the input voltage. So this voltage you can write it down in terms of your current and resistance also. Yeah, so the same thing that we can write it down over here also. You can write it down in terms of this your power gain. Yeah, so that is a P naught upon Pi, then write it down, P is equals to Vi. So this one you can write it down in that form also. So what is this transconductance? So that is a ratio of change in that your output voltage, small change in the collector current to the corresponding change in the base voltage at constant collector voltage. So this is called as a transconductance for this particular case. So you can derive one more relation, that is the relation between IE, IB and IC. So just divide by IC for each term. So IE upon IC, yeah, is equals to IB by IC plus 1. Again alpha is equals to IC upon IE, and beta is equals to IC upon IB. So just put down these values and you will get this expression. So that is beta is equals to alpha upon 1 minus alpha, or you can get that alpha is equals to beta upon 1 plus beta. So that is the relation between the alpha and beta that you will get over here.